So, are most people done with readings, or still trying to finish? Anyone?
I'm done.
Okay, cool. All right. So I apologize. I don't have a wider screen, so we just have to kind of split the screen like this. Anyway, so why don't we start? I think it says in chapter 1, the most common supervised learning tasks are regression, predicting values, and classification, predicting classes. In chapter 2, explored regression tasks, predicting housing values using various algorithms such as linear regression, decision trees, and random forest. Now we'll turn our attention to classification systems. And if you didn't go through chapter 1 or chapter 2, I would encourage you to find the recordings. I think someone pinned the recordings right here. Let me see. Right here, I think Shamsuddin pinned the recordings right here. So feel free to go through those. Okay. So MNIST, and for those of you who are relatively new to ML or machine learning, MNIST is basically a data set, in this case, 70,000 small images of digits handwritten by high school students and employees of the US Census Bureau. And it's basically 0 to 9 as the digits. And each image is labeled with digit it represents. And it's more like the hello world of machine learning. And we typically also use MNIST for multi-class classification, because it has frankly 10 classes. But in this case, we're also using this for binary classification. And in this case, particularly, we're just doing 5 or num5s. Cool. So scikit-learn provides many helper functions to download popular data sets. MNIST is one of them. I guess this is just a scikit-learn's. And let me start running this. Okay. And basically, this is just a function from scikit-learn. And if you do shift tab, you can kind of see what's going on here. Okay, fetching data sets from OpenML by name or dataset ID. And the data set that we use is MNIST 784. 784 stands for 784 pixels. That's 28 by 28. And I don't know what that version means, but I guess it's not.
So a quick one.
Sorry,
where do we find the codes?
Did again?
Where do we find the codes?
You mean this code?
Yes, please.
Yeah, it's in the hands-on GitHub.
I pasted it in the chat.
Okay, thank you so much.
Yeah, it should be this GitHub hands-on ML2. Okay, so someone already pasted it. Great, thank you. And you can see, you can just call like mnist.keys, and it's basically in the end, mnist becomes a dictionary object. And if you call a data key, it'll give you the data. And if you call it target, that's the target variable. And of course, there's like a bunch of other dictionary keys you could call. Cool. So Data sets loaded by scikit-learn generally have a similar dictionary structure. That's what I said. A DSCR key describing the data set, a data key containing an array with one row per instance and one column per feature. A target key containing an array with the labels. Let's look at these arrays. And and you can also check, what kind of methods you can call by just using dir. So that's a pretty handy Python method. Cool. So again, when we call a dictionary, and we can just call the value by its key, right? So if we call data and the target, it would just give us that, and we name it as X for the data and Y as the target variable, and we check the shape by just typing dot shape, and that's 70,000 images. And again, we were dealing with 784 pixels. Let me just kind of, so that's what it looks like. Okay, Y dot shape, again, we have 70,000 images, and each target variable indicates basically the number, the true number that's on the image. And 28 by 28, that's 784 pixels. Cool. So yes, he kind of explained it here as well. There are 70,000 images, and each image has 784 features. This is because each image, okay, we went through that. And again, like 0 is white, 255 is black. So when we take a look at those pixels, we kind of have an idea of how black it is or how white it is. And we'll do that here. Okay, so we're taking just the first image, x0, and x0 is, let me just do it here. That's basically what x0 looks like. And again, like 0 to 255. So, if it's 3, then that's probably very close to white. And when it's 253, then it's pretty close to black. Okay. We want to reshape the data to 28 to 28. And we just call dot reshape. And that's the standard method of an array. And this is just basically mapping the colors to scalars so that it will show actually black and white instead of just numbers. And we want to take out the axis, and we show that it's actually a 5, but like, it could also be like 3, but it's actually 5. Cool. So, any questions? No? Okay, great. So, and it says, note that the label is a string. Most ML algorithms expect numbers, so let's cast the Y to integers. So we're changing all the Y's to NumPy that integer 8, right? It's just a type of integer.
Sorry, Vincent, just a quick question.
Yeah.
So yeah, I just asked it on the chat also. Is like the data set that we have here right now, when we have X and Y, they're just arrays. These are different to the previous chapter where they were a different data structure called data frames.
Yes. So in this case, we're just basically, since those are images, and machines convert the images into pixel values. And if you understand what I'm saying, so basically this would indicate, you know, a RGB value. And in previous chapter, we were dealing with tabular data. And then in this case, we're not dealing with tabular data, we're dealing with images.
Okay, gotcha.
Yep, sure. Okay, so, but wait, you should create a test set and set it aside before inspecting the data closely. The minutes data is actually already split into a training set, the first 60,000 images, and the test set, the last 10,000 images. So we're basically saying we want to use the first 60,000 images as training sets, and the rest of the 10,000 images as test sets. And of course, we're not specifically separating in validation sets because we're going to use cross validation. So when we feed the training set into the cross val score function, the validation set is automatically separated for us in the cross validation. Now, it says the training set is already shuffled for us, which is good because this guarantees that all cross validation fields will be similar. You don't want one field to be missing some digits, and moreover, some learning algorithms are sensitive to the order of the training instances, and they perform poorly if they get many similar instances in a row. Shuffling the data set ensures that this won't happen. Now, I want to bring this to, there's actually pretty important points here to be made. Like, when do you create a test set? When do you do the train test splits? Like, how much EDA should you do like before you like actually do this? And I want to kind of go back into the last chapter. If you recall, the step when Aurélien Jehan sort of started separating the test train sets is right here. Okay, so this is where he started, right? But look at what he did before this. He still did some EDAs, you know, some histograms, okay, and did some like observation and made some comments here. Did some describe value counts info, but only after he split the train test data sets, then he started doing real EDA, like cutting the data, doing more histograms, stratifying, and also visualizing. So that's a very important point because you actually don't want to do too much EDA on your entire data sets, including the test data set. So you should probably do as much EDA as possible only on your training sets and without even observing your test set. So I just want to make that clear. Okay, back to chapter 3. Okay. Okay. Training a binary classifier. Let's simplify the problem for now and only try to identify one digit, for example, the number 5. So we're only detecting 5 or non-5s, and capable of distinguishing between just 2 classes, 5 and non-5. That's right, and true for all 5s. So basically, this will just validate this entire training set. Array, and if it's equal to 5, then it will be true, and if if it's not equal to 5, it will just be like false. Again, for test set, it's the same thing. Okay, so let me run these. Anyone has questions on this? This was just plotting these images. No? Okay. Okay. Then we'll start from here. And if you just type in white trim 5 again, like if it's 5, it would just be true. If it's not 5, it's false. And same thing with the test. Okay. So now let's pick a classifier and train it. A good place to start is with stochastic gradient descent classifier using scikit-learn Sgd Classifier class. This classifier has the advantage of being capable of handling very large data sets efficiently. This is important. Yeah.
Sorry, I have a question. Sorry to disrupt you.
No worries.
You said the EDA has to be performed before the test train splits.
Well, after. Most of the EDA should be done after.
Oh, okay. After the test train splits. But I'm thinking, is it not the same transformations we do to the train set that we would do to the test set? So is it not like are we not repeating like task by doing EDA for the train sets before doing EDA, applying the same transformations we do to the train set, the same data cleaning we'll do to the train set, and then do the same data cleaning again to the test set before we apply the model? Are we not repeating task here?
Well, does anyone want to answer this question?
Oh yeah, I'll take that. So the point isn't that we're doing the same operations to both training set and test set. The point is here about it's a broader point about the concept of data snooping. That means looking at the test data in any way, shape, or form before you have formulated your final model. That is the #1 rookie mistake that people make in machine learning. And so you should take away from this lesson an understanding of what data snooping is and how to avoid it. So the point is that anything you know about the test set from having looked at it can make its way back into the model. And that means that the model will have some knowledge of the test set. That's why you're not allowed to look at the test set. So the thing you have to do is before you do anything, you have to split the data set into test and training parts. Now you're right that the transformations that you apply to the training set are the same as to the test set are the same as the transformation you apply to the test set, with one exception, with one clarification, that is. Yeah, you scale, you have to scale the data often. And when you scale the data in the test set, you must use the parameters derived from the training set. Because otherwise that assumes a knowledge of the test set that you shouldn't have. So if you scale the data and normalize it, whatever, you usually use the parameters, mean and standard deviation, that were derived from looking at the training set. You use that mean and that standard deviation to standardize the test set.
Oh.
Is that clear?
Yeah, that makes sense.
Okay.
Yeah, let me go back to chapter 2 because this is where we actually built an entire full pipeline on this, and we actually, okay, so non-pipeline right here, right? So full pipeline. So we got a non-pipeline and a category pipeline, and it's combined into a full pipeline. And notice that now it's only being applied to training data sets, right? Training set. But like when we try to do prediction, evaluate your system. Okay, here. Full pipeline. So that was the pipeline that we used on our training set. Now we directly apply this full pipeline to transform the test sets, so that it would match our model, and then we do predictions. Is that clear?
That's clear. My only confusion is just like in the sense of, okay, let's take away transformation. When we are cleaning the data set, should we so are you saying that when we just get the data set, split immediately, or after cleaning the data set, you can then split? And by cleaning data set, I mean doing things like converting what are clearly categorical variables from numerical variables into categorical variables, doing things like filling in missing values. So are you saying we should not do that at all before doing, we should not do that at all until after we've done our train test weights?
Yes, and
Yes, yeah.
and as you suggested before, Tochuk, you said that we do the same thing. We're applying the same operations to the training set as to the test set. Oh, I think we just lost the guy who's asking the question.
No, I'm here.
Oh, you're here. Okay. Oh, yeah. So, sorry. So, yeah. So you have a pipeline that has all those operations encoded in it, right? You tell the pipeline exactly how to replace missing values, exactly how to normalize, and so on. So you don't lose anything by having to do it twice. You know, you already have the pipeline, and it knows exactly what the pre-processing is.
Yeah, but I think there's a difference between pre-processing your data to get rid of, NAs, NANs, other missing values that you may not want in your final data set because you might not be able to run your application with those in it.
Yeah, but the pipeline will do that for you. I mean,
right, but what I'm trying to say is, like, if you have, but it's one thing to take out that sort of stuff, but if you say, now I'm going to fill in, missing data based upon all the data, okay, then you're getting into kind of like a question.
Right. That's a really good point, and that's what I was saying before. Is that whatever your pipeline does to the test data, it must be based on parameters that it derived from the training data. So if you're going to replace, a missing value with its median, you have to replace it with the median from the training data, not the median from the. In other words, if you're operating on the test set and you want to replace missing values, you have to replace it with the median of the training values, not the median of the test values.
I agree. Yeah.
If that makes sense. Yeah. So in your pre-processing, you're not allowed to have any knowledge of what's in the test set, and that's why it's best practice to split training and test set apart immediately before you do anything else.
Yeah, and if I can add, and that's why we saw there is the fit, and then there is the transform, and the fit transform. Yes, we can do like the fit transform to the training, but like whenever do the fit transform to the test set, we only do transform, right? Because it's transforming on what was fitted in the training.
Mm-hmm.
That's a good point. Yes.
Yeah, and the one point I'd like to make for people who are kind of new to ML is we get these data sets that are prepared for us with training and tests already available. Just think of your test set as future data that you don't even have access to. That's really what it is. It's future data that's going to come in through a website or an app or something like that you can't even rely on. So that's one of the main reasons why you focus on the training set.
Right, and if you don't do that, if you don't follow Brian's advice, what will happen is that you'll fool yourself. If you look at the training data or use some aspect of the training data and you're not following this rule of a firewall between the test and training data, if you use the test data in any way, you'll get a model that's much better than it should be. And then when you apply it to real data, you'll be very, very disappointed, and so will your boss. You know what I mean?
I guess I just have one more final question because I'm doing a research on fraud detection in energy consumption, and I was given train and test data sets, right? And now, are you saying do I still need to perform a split on the train data set? Or should I just treat the entire train data set as train data sets for what it is?
Well, when you do cross-validation, it automatically splits the training set into the folds, into the folds of the cross-validation. So there you can do your modeling and you can do your hyperparameter tuning. But you will first set aside the test set and just regard it as completely sacred and untouchable, and you can't even look at it. So that's the first thing you have to do.
So, and to just add on that, just think that there are like two splits. There is the first initial split of the training and test set, and that's what everyone is talking about. And the last one that Joseph just mentioned, which is like more of a split for cross-validation,
Yeah.
Okay, so just, yeah.
Cool. Okay, so let's keep going. Basically, we picked the Sgd classifier, but Sgd classifier actually is in itself is not a classifier, but it has a default setting. And as I digged into it, okay, I mean, it just stands for like stochastic gradient descent classifier. So in itself, it doesn't tell you which classifier it actually uses. Now, but underneath, it's SVM or logistic regression and so on. Now, when you don't specify, it will just resort to SVM as the default. So, and it says right here, the model it fits can be controlled by default. It fits a linear support vector machine. So, and that's what we're using. We're not sorry. We're not specifying any specific classifiers. We kind of just resort to the default SVM right here. Okay, and the max iter is a number of epochs, and also it just uses L2 penalty as the default. TOL, that's stopping criterion. If it's not none, training will stop. You can dig into some of the parameters, but that's kind of the default parameters that he used. Cool, and the reason why we set 42 as random states, which he will explain right here, the Sgd classifier relies on randomness during training, hence the name stochastic, and stochastic just means random. If you want reproducible results, you should set the random state parameter. In this case, we're setting this as 42, but you can set as any numbers you want, as long as you set a number. Okay.
And for those of you who are wondering why it's 42, this is coming from The Hitchhiker's Guide to the Galaxy, where 42 is the ultimate answer to the question of what the meaning of life, the universe, and everything.
Really? I didn't know that.
That's my favorite.
That's cool.
So one doubt I had here, sorry to interrupt. So in the, when you open the Sgd classifier, there it was showing that if you set the loss function, that itself is like kind of setting the model, like SVM or linear or like.
Yeah.
So like which kind of loss function should, like, I think SVM is using some hinge, I think. I'm not sure.
Yeah, hinge right here. It says
Okay.
defaults to hinge, which gives a linear SVM.
Okay,
And if
so
you use it log, that's log.
Logistic.
Yeah, logistic.
Okay.
Yeah.
Cool.
Yeah. Yeah.
So hinge is a L2 penalty.
It says L2 penalty, but
cool.
you don't have to use L2. You can use L1 or elastic net.
Oh, I don't know the loss functions of SVM, so maybe I'll refer to that. Okay, cool.
Sure. Okay. Now we can use it to detect images of the number 5. And again, we pretty much instantiated object and we fit that, and now we can predict on one image. Again, this was just x0, right? Like the first image, and it's number 5. And like, is it true? Is it number 5? Great, it says it's true. And when we run that, it'll take a little time.
Just a question there. I'm sort of actually using the same seeds and all, but I'm getting a different output. So when I do an sgd dot predict of some digit, I'm getting the answer by default as false. Do you know why that could happen?
What's your sum digit value?
It's 5, I guess. I'll have to check.
No, that's the thing you need to check. It's probably not 5. That's why it's saying it's false.
Yeah.
Or it could just be classifying it wrong. I mean, because it's not 100% accurate, right?
That's true. But
the important thing to realize is he converts the labels to a true or false by executing the code earlier, where he creates
right
why
here.
Test is and why train is.
Mm-hmm.
So that's why, given the input that you supply through some whatever value, then it will tell you or predict the corresponding label that it should have.
Yeah, Srinivas, my sum digit is 5. I just verified.
Okay, so you can double check if your y train is 5 and y train equals double equal sign 5 right here.
Yeah, all that I just followed as is.
Yep, then it's just predicting incorrectly, so which we'll see that it doesn't always predict correctly.
True.
So
yeah, then it's just, yeah. Okay, so let's keep reading. The classifier guesses that this image represents a 5. True, looks like it guessed the right in this particular case. In your particular case, it didn't. Now let's evaluate this model's performance measures. Evaluating a classifier is often significantly trickier than evaluating a regressor. So we will spend a large part of this chapter on this topic. There are many performance measures available, so grab another coffee and get ready to learn many new concepts and acronyms. Good way to evaluate a model is to use cross-validation. And this is probably the second time we're coming across this huge concept, cross-validation. We already did that in chapter 2. If you don't know what that is, I would encourage you to go back to chapter 2 or read more on sklearn cross-validation. Again, this is a great post on cross-validation, so I would also read a little bit on this. And let me just post this on chat. Okay. Great. And he actually implemented cross-validation, and I thought that was really cool. And let's go through that. So well, first of all, he imported stratified k-fold. And basically we're using stratified sampling, but we're also using, and we can specify how many folds we want, or how many splits we want. So n splits equals 3. That means we wanted 3 splits with stratified sampling, and we want reproducible results. So again, we're setting the random state here. Now, for every single split in this for loop, okay, we're gonna generate some indexes with that. Now, what does this mean? We're importing a clone function from sklearn.base. What does this mean? We're cloning the estimator at the beginning of each for loop. So we're literally cloning this Sgd CLF, and it's after fit, of course. So we're cloning this object and we're using, we're basically getting the indexes and passing them into the variables and fit the clone model with the split data from k-folds. Okay, so we're fitting that and predict the data and summing up all the correct predictions and get the accuracy. So that, by using number of correct predictions divided by all the predictions. So and we're doing 3 folds, 3 splits, so we're getting 3 scores. And as you see, like we're actually improving a little bit, 0.95, 0.96, 0.96.05. Okay.
When can I had a doubt actually in the previous
Am I the
cell.
only one who's not able to hear it?
Hello?
Hello.
Yeah.
Yeah, I had a doubt in the previous, in the previous cell itself, like the sum digit part.
Some digit part. Okay.
Yeah.
What was your question?
So I wanted to understand, like, what is sum digit here? Like, is it like it shows that it is number 5? So, but is it like a particular number 5 in the test set?
Yeah, no, it's actually the first one, the first image. This is some digit.
Okay. It is
Yeah.
first digit. Okay, yeah, that's
It
what.
is the first image
In the
or array.
In the training set.
In the training set, yes, X.
Okay, so we are predicting that. So if I, for example, if I'm setting the same seed like 42, should I get the same result for like the classifier?
What do you mean?
I mean, like if I keep 42 as a same seed, so
in general, if I may, in general, yes, but in this case, only with this MNIST data set, they're already provided in order. They've already pre-processed it, they've cleaned it up, they've kept all the digits in order. And so we're just going with some digit equal, the first image is 5, and we're just going with that. In this, it's just for this MNIST example. It's prepared so well, that's it.
I just wanted to like understand whether it will yield a different result even if I set the random seed as the same. Like I just wanted to know like if the result will be reproducible like that, because Srinivas had asked that it's a bit, not Srinivas, I think someone had asked that it's giving them a different result, right?
I think so. If I'm understanding you correctly, are you saying, let's say, even if we set this random state as 42
Yeah.
right here,
Right.
and if we train this again, will we get the same score?
Okay, maybe the score, I'm not asking for the score, I'm asking for that particular value, so it could yield a different result, right?
Particular, what value?
The first value, x0, the sum digit which we showed. If we use predict on it, it could yield false as well. Like,
Well, in this, in this case, we're just shuffling this. So some digits changed already, like because we're already shuffled.
Okay.
Yeah.
Cool.
And before we were just taking a peek at what it was like, and doing a little experiments on the first image.
Okay, cool.
Yeah.
Cool.
Hey, I had a question.
Yeah.
The cloning is done on the untrained classifier, right? Not on the trained one.
Well, it says clone does a deep copy of the model in an estimator without. Yeah, go ahead.
Initially, we trained on the whole trained data set. We don't want to do that, right? We don't want it to look at the validation set. So
It
every time
says it yields a new estimator with the same parameter that has not been fit on any data. Okay, so that answers the question. It has not been fit on any data.
Right. Okay. And I had one more question. So I thought that during cross validation, like you train on, suppose you have 5 folds, you train on 4 folds, and then you predict on the 5th fold, right?
Correct.
And then you don't use the good model, you start afresh again. Is it like that? I mean, that's what it looks like from this loop. But what is wrong if we just use the good model and then make it even better and then make it even better? Like, did you get my question? I think that's how it should be done, right?
Yeah, that's a good question. Does anyone have answers?
Yeah. From here, it looks like we start afresh every time.
Yeah, it looks.
Well, the reason for that is that you want to see how well the model performs on data that it wasn't trained on. Like, so you're trying to get an estimate of how well the model will do on.
I got it. Yeah. Yeah. Then you will have seen the validation set, right? Yeah, I got it. Yeah. Yep.
Okay. Cool.
But another
Thanks.
way would be to just say CLF. You could just call it CLF, and then you could say CLF equals none before you start anything. And then every time when you change the model or do something else, you start from scratch by saying CLF equals none. So I don't think you need to clone the classifier. I could be wrong. If anyone thinks I'm wrong, I'm welcome the discussion.
If it's none, then how would you? It has to be an estimator object, right?
Yeah, but you start off by saying CLF equals none, which basically erases whatever was in it before, and then it's starting from a clean slate, and then you build the classifier from there. So then you would say CLF, you would say, first you'd say CLF equals none, and then you would say CLF equals SGD underscore CLF.
Right. Yeah. Okay.
Okay.
And then you wouldn't have to use the clone function. But I mean, this is fine. I think it's fine to use the clone.
Cool. So let's keep going. We are running out of time. Stratify K-fold class performs stratified sampling to produce folds that contain a representative ratio of each class. Again, that's just what stratified sampling means. At each iteration, the code creates a clone of the classifier, trains the clone on the training folds, and makes the prediction on the test fold. Then it counts the number of correct predictions and outputs the ratio of correct predictions. Cool. So let's use the cross-fail score function to evaluate our Sgd classifier model. So using K-fold cross-validation with 3 folds, remember that K-fold cross-validation means splitting the training set into K-folds, then making predictions and evaluating them on each fold using a model trained on the remaining folds. So I guess that answers a couple of the questions previously. Cool. So did I miss code block? Okay. So basically, we train on this, and we're now just evaluating. Use the cross-val score function from model selection from sklearn, and we're using CV equals 3. We're using scoring equals to accuracy, and we're using this model. We're evaluating this model that was trained, and those are some of the labels and also the training data. Wow, above 93% accuracy ratio of correct predictions on all cross-validation folds. That looks amazing, doesn't it? Well, before you get too excited, let's look at very dumb classifier that just classifies every single image in the not 5 class. That's here. Basically, we're saying, okay, fit is just pass, and predict what it just returns numpy.zeros length of the training data, and so basically 60,001, that's the dimension of all the zeros, bunch of zeros. But then you only use d type equals the Boolean. So basically, it's just creating a NumPy array with all falses, as zeros get evaluated by d type equals the Boolean. Hence, it's basically predicting every image to be not 5. And again, this is what it looks like.
Sorry, Wenchang.
Yeah.
I have the same question again. The cross-file score would take in the untrained classifier, right?
No, it would actually take the trained classifier, because you are now evaluating a model.
So the training part is not implemented by cross-file score.
Sorry, say that again.
From the documentation, it looks like the estimator should be the object to use to fit the data.
Does anyone have answers? Is it trained or not trained? I'm a little confused as well.
I believe it trains. I believe it's a.
Can you just open the documentation of cross-file score? Just real quickly.
Okay, so why don't we do that? Sklearn.
Because all it gets as input is the training set and the training labels, so it has to train.
So it's untrained, right? The Sgd class, the estimator.
Yeah, I mean the cross-val score uses the training set and the training data and the training labels, and it makes 3 different models and trains them and then predicts with them. So it does everything.
Wenchang is the first is the first argument estimator.
Yeah, the first argument is the
the object to use to fit the data. So I guess it does as well, right?
It must be, yeah. It's probably still. It will probably be trained again, like under cross-val score, if I'm understanding this correctly.
But okay.
Oh, I thought that's what we were. I thought that's what you were asking about. Cross-val score is what does the whole shebang. It trains and predicts. It trains. Well, it splits into 3 folds. It trains 3 different models, 1 on each fold, and then it predicts from each of these models on the rest of the data. That's
so
that's outside the fold.
One, right?
So you don't. Oh, I'm sorry. Yeah. I wonder if Sgd underscore CLF is.
It refits the data.
Well,
so when it says it fits the data, it means it refits it. It means it creates the
but
model.
Then if we have already
trained, you pass it the trained classifier, but then when it clones it, it actually makes a copy that is reinitialized. So that's why it basically retrains it every time.
So I guess it goes back to this. It clones every time, and so this is it.
Yeah. So clone basically forgets the training state, and it goes back to like a randomly initialized.
Without actually copying attached data. It yields a new estimator with the same print that has not been fit on any data. So it would initialize every time. And this is, it says, this is, the following code does roughly the same thing as sklearn's cross-val score function, and it prints the same result. So again, so I guess Isaac is correct, and thank you, Isaac. Yes, so it reinitializes every single time, and it does not, it only passes almost like an empty object. So it only passes this rather than like this. Is that clear?
Yeah.
Okay,
so
great.
cross-val score does not give you back a trained classifier, right? It's just used to get a validation score.
That's right. Yeah. Yeah.
Okay. So what did not make sense to me was if you have already trained on the training data earlier, so it has okay, you make it, so once you clone it becomes a untrained classifier again. Okay.
Right.
Yeah, I
Right.
think I got it. Okay.
Right. Okay. Great.
Thanks.
Sure. And okay, so let's get back to this. And it says, well, before you get too excited, let's look at very dumb classifier. And that's right, it has over 90% accuracy. So basically, this classifier only predicts everything to be not 5. And it still has over 90% accuracy. This is simply because only 10% of images are 5s. So if you always guess that's an image is not a 5, you would be right 90% of the time. And so this comes back to this skilled data set problem. And this demonstrates why accuracy is generally not the preferred performance measure for a classifier, especially when you're dealing with skilled data sets. Anyone want to add to this in terms of how people like in practice balance the data sets?
Hey, can I jump in here, because this is actually my thing?
Yep, please.
So what he's saying as a skewed data set, skew means something else. What he really should be saying is an imbalanced data set. Okay? Data sets can have balance or be imbalanced. And when you look at the different classes, the classes determine the balance. So say, for example, that you have the MNIST data set with, you know, the training set has 60,000 digits from 0 through 10, right? 0 through 9. So there are 6,000 instances of each digit labeled. That data set is balanced. Now, if you had, for some reason, created a MNIST with 6,000 of every single number except for number 9, and you only had 10 nines, you'd have an extremely imbalanced data set, okay? And that is going to cause a lot of issues and problems with classification, and also which formula you use. So the whole thing he's talking about with accuracy is called the fallacy of accuracy. And that's what he's trying to show you here. You can get great accuracy if you have an imbalanced data set. So what he's done is he's taken all the examples of number 5, right, and wiped them out. So now you have a data set in which you have 6,000 examples of every single number except for number 5, of which you have 0. So you have an extremely imbalanced data set. And you run through it, and it doesn't work. I mean, you get a 90% accuracy, 91%, but because you have no examples, and the way the formula is, you end up getting a good number. I actually posted the formula for accuracy on the Slack, if you guys want to see it. So
okay. So if I can just add like to that imbalance, I mean, yeah, I'm sure we always cross imbalanced data sets. So what I want to mention and what I want everyone to remember, like again, the example, just dogs and cats. Think, for example, you have 9,000 dogs, but you only have 1,000 cats. That is an imbalanced data set. So how would you really then kind of like work with that? So you would think of two things. Either you would like to downsample those 9,000s to be kind of like the same number, so we'd have 1,000 and 1,000, you know, or maybe there is a way that you would like to oversample the 1,000 to kind of maybe to like 2,000 or 3,000, and with that there's something else that maybe we're going to discuss. There is also, instead of just replicating them the same, maybe you can just add some tweaks like data augmentation. So you can get to data augment your data, like your little class to maybe 2,000 or 3,000. And you can also maybe drop the 9,000 to 3,000. And then now you have a balanced data set. The only catch is when you downsample the 9,000, for example, to the 1,000, you also want to make sure that you're not biased, because like maybe the 1,000 that you have does not really represent all the 9,000. So just that's something to keep in mind. Yeah,
good point.
And another thing is that when you downsample, suppose you have only 1,000 positive examples and 9,000 negative examples, so you want a balanced data set. So you downsample the negative samples to get only 1,000. Well, you're throwing away 8,000 data points, and that's not good. So that's the trade-off. You get a balanced data set, but you've also thrown away a lot of data. Whereas the other technique that Salim mentioned, which is oversampling, where you keep the 8,000 negative data points, but you oversample the 1,000 data points. You just keep pulling more and more randomly out of the data points that you already have until you have 8,000 positive examples. And now you have a balanced data set. That isn't the ultimately great solution either, but those are the two main solutions that I've seen. But there are more sophisticated ways to do it as well, like as Salim mentioned, data augmentation is one.
Cool.
Yeah, I mean, the papers on this, subject seem to indicate, obviously it depends how much data you have. If you have a ridiculous amount of data, if you have like 1 billion cases versus 1 million, well, you can undersample and discard, the balance of the billion. You still have 1 million cases, and maybe you know that you only need 100,000 to get accurate results. Conversely, for most things that we're working with, it does seem that oversampling beats undersampling in the published literature, and that's just what I've found.
And then there's the data augmentation, for example, is you might take, like, if you're dealing with tabular data, you might take linear combinations of your columns to generate new columns or something like that, sort of to generate new samples. You could take linear combinations of the columns of 2 samples and then generate a third. And so that's another way to augment to get more positive examples.
At what point do you think it would become a problem when something is unbalanced? Like is it like 60% or 10% or?
Yeah, it's more like 10%. And you could ask Tochukwu, because he said he was dealing with fraud detection and anomalies, and anomalies are things that happen very rarely. So by definition, you only get very few examples. So I wonder what Tochukwu would say about that.
He also, this Prasad. I also work on a similar field. I work on credit conditioning and the fraud decisioning. Typically, we want the fraud to be in real time. We want the fraud to be less than 1%. That's the ideal scenario for the business, but it makes very difficult from the data science standpoint. So what we do is, like, we do all sorts of upsampling, downsampling of a majority class, modding, and all those things. But one of the things that I found it to be very useful is, it depends again on what problem that we are, how we are actually doing a sampling. Upsampling is a technique, but how you do it, do you do it at a transaction level or a user level, really actually help us increase the accuracy, or what are the metric that we are actually measuring. But what I found it to be useful is, in scikit-learn, we do have something called as a class weightage. Playing that class weightage has given me a better result comparatively to doing all sorts of random samplings.
Do you mind if I ask you, are you using accuracy, the actual accuracy measure, as your metric?
No, we don't use accuracy because it's a skewed data set. And for example, if I blindly predict everything as a non-fraud, I'll hit more than 99% of accuracy, and at a high level. But what we do is, like, we create a stratified samples and look at various metrics. Not only just more mathematical matrices like precision and recall. We also look at business metrics. So not all fraud will be of equivalent importance for the business. So
Okay.
Yeah.
So guys, going back to the point
Go
of
on.
the lecture of the skewness, which maybe what he should have called maybe the imbalanced data set. So there is just another way that's also very common that I just want to share, and it's called upweighting. So what you would do, for example, going back to the 9,000 versus the 1,000, you can also issue the 1,000 samples higher weights than the, so and then what you, and then it is very similar to kind of like oversampling and downsampling, but now you're just playing with those weights. So that's also a very common method that we use.
One more thing I wanted to add. So I previously Prashant was speaking, somebody who was speaking related to this thing. So I came across this problem where there were numerous categories in the dataset. Like that was a lone dataset in Kaggle. So in that they were using something called cat boost. So there they talked about mean hot encoding or something like that. So that one, they were in that particular data set, we had we had to predict bad loans versus good loans. So bad loans was exceptionally low number of points in the data which we want to predict in. So that was very imbalanced data set. So there they use cat boost. So can anyone like talk about like that thing? Is it similar to what we are trying to do? Like, will it solve the problem if we use that instead of upsampling or downsampling?
Your question was about cat boost?
Yeah. So there he's talked that if we have highly imbalanced data sets, cat boost solves that problem. And in that there was certain argument which we have to put for imbalanced data sets.
Yeah, so cat boost is a gradient boosting algorithm, and it's a whole package actually, and it's built to be compatible with scikit-learn, and so it has its own methods that you can use. And yeah, it does have methods to deal with imbalanced data sets. But mainly what cat boost is an implementation of gradient boosting, and it's actually the best around right now, as far as I know.
Exactly, and to follow that, so within cat boost, for example, you can find a method for upweighting the dimension or something like that. Yes.
Yeah, there is an argument for imbalanced data set. Something I'm not remembering that. Yeah.
Cool. We probably have to keep going, just so we can finish as much as possible. But thank you so much for the discussion. That was really great. Confusion matrix. A much better way to evaluate the performance of a classifier is to look at the confusion matrix. A general idea is to count the number of times instances of class A are classified as class B. For example, to know the number of times the classifier confused images of 5s with 3s, you would look in the 5th row and 3rd column of the confusion matrix. To compute the confusion matrix, you first need to have a set of predictions so that they can be compared to the actual targets. You can make predictions on test sets, but let's keep it untouched for now. Instead, you can use the cross-val predict function. And this is where he kind of introduced the cross-val predict. I thought it was really interesting. It's basically generate cross-validated estimates for each input data points. So instead of doing a score, calculating a score, you are outputting predictions. Okay, so that's the difference. And it's computed with an estimator fitted on the corresponding training sets. Cool. So let me go back here. Just like the cross-val score function, cross-val predict performs k-fold cross-validation, but instead of returning the evaluation scores, it returns the predictions made on each test fold. This means that you get a clean prediction for each instance in the training sets. Clean meaning that the prediction is made by the model that never saw the data during training. Okay, and now you're ready to get the confusion matrix using the confusion matrix function. Just pass it the target class ytrim5 and predicted class ytrim predict. Okay, great. So Now, each row in the confusion matrix represents an actual class, while each column represents a predicted class. The first row of this matrix considers num5 images, the negative class. 53,057 of them were correctly classified as num5s. They're called true negatives. So this is true negative, while the remaining 1522 were wrongly classified as 5s. That's false positive. The second row considers the images of 5s. That's positive class. 1325 were wrongly classified as num5s. That's false negative. That's false negative, while the remaining 4,096 were correctly classified as 5s. And that's true positive. As a perfect classifier would have only true positives and true negatives. So the confusion matrix would have non-zero values only on its main diagonal. So it basically look like this when you actually just, use the predictions to equal all the labels, and you would just have like everything correctly classified. Okay, so.
Can I just interject something?
Yep, go ahead.
In real life, just be aware that the way that scikit-learn outputs the confusion matrix may not be the way everybody else uses it, particularly in the sciences.
Yeah.
We put our true positives in the first box.
Yeah. Yep.
So it's basically about the opposite. So if you don't know that, you're going to go completely down the tubes on a confusion matrix when presenting it to anybody who's a decision maker, and they're going to be very confused. Just letting you know.
Right, right.
Yeah, Wikipedia reference also flips it, and it's probably the best explanation of all of the different names and the different values if you look for Wikipedia confusion matrix.
And to add, but usually you would add the access like actual and I mean not actual and predicted, and also like the positives and negatives. Wouldn't you usually like have that on the side? You would, right? Yeah. So yeah, so yes, I think they have it flipped, but like even if you have the accesses there, I think you can still make sense from it.
Yeah, I think there is the plot confusion matrix, which I don't think is shown here in the lesson, but I'll just put the link down here in the chat. But that gives you more of like a plot with the labels and everything. That makes it more clear.
Yeah, yeah.
So I think here so the definition of the confusion matrix, the way he gives it, is that the rows are the actual classifications, and the columns are the rows are the true class labels, and the columns are the predicted class labels. And in this case, a label of 0 means means not a 5, and a label of 1 means a 5. So it's basically going by 0, 1. Column 0 and row 0 is not a 5, not a 5. So you just have to be aware of what the definition of your particular confusion matrix is. In other words, you should be able to say what any element in the confusion matrix is telling you. What is row 1, column 1 telling you? What is row 2, column 1 telling you, and so on.
Let me just check the help to see. Okay, so I guess it probably says something here. Okay, but I kind of label here just so everyone kind of have a good sense. This is true negative, this is false positive, this is false negative, this is true positive. Cool. So, and we're getting to the precision, which is true positive divided by true positive plus false positive. And that is basically the accuracy of the positive predictions. Basically, how many true positive do we have out of all the positive predictions we have made. Okay, so TP is, yeah, okay. A trivial way to have perfect precision is to make one single positive prediction and ensure it's correct. But this would not be helpful, and since the classifier would ignore all but one positive instance of precision, it's typically used along with another metric called recall, also called sensitivity or the true positive rate. This is the ratio of positive instances that are correctly detected by the classifier. So basically what it means is out of the number of actual positive data points, how many of them are true? And that's what recall means. Okay. If you're confused with the confusion matrix, figure 3.2 may help. And this is kind of how he puts it. And again, I think someone else mentions, Stephen mentions, you know, there's different ways to kind of lay this out, but you know, it's essentially the same. But like, don't miss the labels. Don't get the labels wrong. Okay.
Maybe.
Someone said something.
Oh, sorry, I have to mute. Sorry.
Sure, no worries. Precision and recall, how do we get that? Scikit-learn provides several functions to compute that, and we can just import that from metrics directly and calculate that by passing in the true labels and the predicted labels, and that's how we calculate a precision score. Now, I mean, since I'm not, like, this is actually the numbers from the book, so it actually doesn't match. But if I use numbers from here, it should. This is basically, again, calculating precision score. And again, recall score doesn't match this because this is the number straight from the book. This is the number that's after training on my end. So, okay. Now your 5 detector does not look as shiny as it did when you look at its accuracy. When it claims an image represents a 5, it's correct only 72%, 73% of the time. Now, moreover, it only detects 75.6% of the 5s. Okay, it's often convenient to combine precision and recall into a single metric called the F1 score. In particular, if you need a simple way to compare two classifiers, the F1 score is the harmonic mean of precision and recall, whereas the regular mean treats all values equally. The harmonic mean gives much more weights to low values. As a result, classifier will only get high F1 score if both recall and precision are high. So F1 score is a pretty balanced way of combining both precision score and recall score. And it's usually a score that's widely used to do classification jobs. Anyone wants to add something to this F1 score?
So I'll just mention that the F1 score is the harmonic mean of precision and recall. And F1 is good because it works fine in cases of class imbalance as well as balance. So you can use it pretty much all the time. The only problem with F1 is that F1 doesn't incorporate the measure of true negatives. That may or may not be an issue depending upon what you're doing. F1 is particularly useful for segmentation, where you have basically an infinite number of, if you segment things a certain way, you can have an infinite number of segmentations. So you really don't have any true negatives. So it kind of goes away in the equation. So it's really good for that. So if you're concerned with the negative case, F1's not the best score. If you're only concerned with the positive case, it's pretty useful.
Mm-hmm. Yeah, so and it actually talks a little bit here. The F1 score favors classifiers that have similar precision and recall. This is not always what you want. In some contexts, you mostly care about precision. In other contexts, you really care about recall. For example, if you trained a classifier to detect videos that are safe for kids, you would probably prefer a classifier that rejects many good videos. That means low recall, but keeps only safe ones, and it would mean high precision, rather than a classifier that has much higher recall that lets a few really bad videos show up in your product. In such case, you may even want to add a human pipeline to check the classifier's video selection. On the other hand, suppose you train classifier to detect shoplifters in surveillance images. It's probably fine if you classifier has only 30% precision, as long as it has 99% recall. Sure, the security guards will get a few false alerts, but almost all shoplifters will get caught. Unfortunately, you can't have it both ways. I thought this was really interesting when I first learned it a couple of years ago. Like, increasing precision reduces recall and vice versa. So you don't really get it all, and there's usually a trade-off, just like variance and bias. Cool. Anyone wants to add anything before we move on?
Shang, quick question. If you go scroll up a bit, yeah, there you go. I noticed that he's scoring the F1 score on the training labels and the training predictions. Is that because we haven't really created a validation set? I mean, I'm used to doing this on the validation set, but I guess in this case, because of cross validation, there isn't really one validation set.
Right. Yeah. I think that's the reason. Yeah.
Okay.
A quick one. Where do we check this video? Like, if we need to watch it again, where do we look for it?
We'll be
posting. Yeah, we'll be posting the recorded video within a day, and so let's see. I think it was mentioned. I think Wenchang mentioned that someone has taken it upon themselves to actually put a whole list. Yeah, a whole list of all the recorded videos, and he's going to keep up with it.
It's pinned. It's pinned
yeah,
here.
it's pinned to the channel. There you go. Yeah. So you can always find a complete list of the recorded videos. I think that's a really great idea, and thank you to whoever is doing it. I think it's Shamsuddin.
Yeah, Shamsuddin. Thank you, Shamsuddin. Appreciate it. Okay. So let's keep going. Precision recall trade-off. To understand this trade-off, let's look at how the Sgd classifier makes it classification decisions. For each instance, it computes a score based on the decision function. If that score is greater than threshold, so this is where he introduced the concept of threshold, because you always want to kind of set a threshold to actually predict the class, right? Because you know, if it's 0.7, if it's 70%, well, is it really like a positive class or negative class? You know, you kind of have to set your own threshold. It assigns the instance to the positive class. Otherwise, it assigns to the negative class. And this graph kind of shows nicely on, like, basically how the positive how these performance metrics actually shift when you like shift the thresholds. And this is kind of like this kind of comes in handy when you actually deal with different cases, you know, different business cases, like what it was mentioning before, because sometimes you want to shift the thresholds towards the right, and sometimes you want to shift towards to the left, to kind of increase the percentage of the true negative predictions. Cool. And it says basically, okay, shows a field. Okay, figure 3.3 shows a few digits position from the lowest score on the left to the highest score on the right. Suppose the decision threshold is positioned in the central row. You will find true positive extra fives on the right of that threshold, and one false positive actually is 6. Therefore, with that threshold, the position is 80%. So here, that's 80%, and you have recall of 67%. But out of 6 actual 5s, the classifier only detects 4. So the recall is 67%. If you raise the threshold, the false positive, the 6 becomes a true negative. So when you raise the threshold here, and now the 6 becomes a true negative, thereby increasing the precision up to 100%. So all these 5s are correctly predicted as true positive. So it becomes 100% in terms of precision. But one true positive becomes a false negative, decreasing a recall down to 50%. Conversely, lowering the thresholds, if we shift the threshold towards here, it would increase the recall and reduce the precision. Any questions?
So the one thing to point out is that the thing that makes this all possible is the fact that the classifier outputs not only a class, but when you predict, but it also outputs the probability of the prediction. So so it'll tell you, I think it's class 1, I think it's a 5, and I also think it's 80% probability of being a 5. So that's what we're doing in the x-axis here. We're looking at the thresholds are the probabilities. So you would normally set the threshold at 0.5, 0.5 at the middle, but you can actually set the threshold to make the decision. You could set that threshold anywhere you want, and that's what we were just talking about. What happens when you change the threshold? You get a different precision and a different recall.
Right. Great. Thank you, Joseph. And in this case, it's the threshold is 8,000. And what does it mean, 8,000? I looked it up.
Oh, it's not raw probabilities then. It's just a score. So the classifier is outputting a score. Yeah. Okay.
Yeah. It's confidence score. Let me just.
But you could actually probably convert it to a probability by normalizing it by its maximum.
So what it actually does is it calculates the signed distance between the hyperplane and the current point that we are trying to predict, and that's the score it outputs.
That's right.
Yeah. Okay. Is that a Euclidean distance then?
I'm not sure. Most likely.
It has to do with SVM. I forgot this.
It's a perpendicular distance to the hyperplane at the SVM. That's
oh yeah, that's right. That's right.
It's the linear SVM.
That's right.
So what's it? I missed it. Sorry.
Yeah. I was going to make a point, and I just want to mention that in industry sometimes we would like to optimize for like a specific precision number, or we would like to optimize for a specific recall number. So for example, instead of, for example, of going like, let's say our goal to be maybe 80 precision and 80 recall, maybe your boss would tell you, well, you know what, I care about 90% precision, even if the recall, for example, is less than 80. So that's something that you may often hear. I just want to mention that. Yeah.
So when you do this, you're looking, I mean, we'll actually see it later on in the chapter. You're looking at a ROC curve, and a ROC curve is basically a graph of the recall on the vertical axis against 1 minus the precision. I believe it's 1 minus the precision on the horizontal axis. I think that this I can check this, but I believe it's 1 minus precision. Basically, on the horizontal axis, it's specificity. Okay, yeah. Yes. So basically, 1 minus specificity is the false alarm probability.
Yeah, you can think of them as just TPR and like the true positive rate and the false negative rate.
False alarm rate. So that's what we're plotting here: the false alarm rate versus the recall. And so what you'd normally get is a graph like this for a given model. And as someone was just mentioning, I think Salim, you're okay. And then recall, the maximum, the maximum you could ever reach is 1, right? And this one could go from also 0 to 1. So your boss could ask you, I want you to optimize this for the highest recall that you can get with better than 3% false alarm rate, right? So on the horizontal axis, false alarm rate, it can go, so you might have like, here is 1% false alarm rate. you know, so your boss might, and here's a 2% false alarm rate, and your boss might say, I want you to give me the best recall with smaller than 3% false alarm rate. So that would be, sorry, this is a mess, but it's hard to write on this thing. Anyway, so when you do that, what you do then, and here's 3%, you go up to the, this is called the ROC curve, the ROC. We'll see it later in the chapter if when we get there. But what your boss is asking you to do is get me the best recall you can with better than 3% false alarm rate. So what he's saying is, give me something, get me look at only recalls in here, but I want the best one, so that's this one. So that's kind of like where you'd want to operate your model at the 3% false alarm rate.
And that would be the threshold you pick.
Yeah, the 3% false alarm rate.
Yeah, and the false, to be clear, the false alarm rate is calculated as the false positives divided by false positives plus true negatives. So that's how you calculate it.
Yeah, false positives divided by all positives, right? That's what the denominator is. It's true negatives, which let's see, it's false positives in the numerator, and on the denominator, let's see.
Denominator should be false positive plus true negatives.
Oh, okay, false positive plus true negative. That means, oh, okay. I have to think about the interpretation of that denominator.
The interpretation is basically for all the things that you have that are
all negatives.
Negative. That are negative.
All the negatives. All the
condition negative.
Yeah.
Whether you predict it correctly or not.
Yeah.
But like true, all the negatives basically. Yeah. All the actual negatives.
Yes. Okay.
Yeah. Okay. Let's keep going.
Let me erase that then. Boom. Clear.
Cool. Okay. So Cyclin does not let you set the threshold directly, but it does give you access to decision scores. And that's what we were looking at, the 8,000, right? So that it uses to make predictions. Instead of calling the classifier's predict method, you can call it its decision function method, which returns a score for each instance, and then use any threshold you want to make predictions based on these scores. So, and that's what we have here, and we specify that here. And later on as well. Okay, so you know, when we first set 0, then this is true, and the way how you get the decision score is again this decision function, but when we set the threshold to be 8,000, this becomes false. Because the score is actually 2412, so it becomes false. Now, this confirms that raising the threshold decreases recall. The image actually represents a 5, and the classifier detects it when the threshold is 0, but it misses it when the threshold is increased to 8,000. How do you decide which threshold to use? First, use the cross-val predict function. And so now in this case, cross-val prediction, instead of giving you all the predictions that you need, it's giving you all the decision scores, the confidence scores from the SVM. And you basically use that to plot. And so basically, now you call the precision function right after that. And let's just precision recall curve, and this is the precision recall curve, and it basically computes all the pairs you need for different probability thresholds. So basically, when you have all the thresholds that you have, and you get all the precision scores and all the recalls, and you can kind of pair them together and plot them on the same graph, and this is the boundary of the threshold, and this is the how your precision score and how your recall score varies between the boundaries.
Right. Does anybody know whether whether Sgd Classifier has a predict underscore proba method? Because I thought it had a I thought it always had a predict proba method, and if it has a predict proba method for this model, for the SVD linear SVD model, then it would be really more intuitive to use that instead of the threshold. But anyway, I don't know. But the point is that the threshold is the score. The score which you're plotting along the x-axis is a measure of how confident you are in your prediction.
Yeah, because I mean, when we do random forest, it actually has the predict proba, but I don't know if it has.
We have
one
in
here.
SD as well.
It has it here as well?
Yeah, we have both predict proba and predict log proba.
I see. That's good. I mean, yeah. So if you did an if you wanted to play around, you could plot the probability versus the recall and the probability versus the precision, and like that in a plot, and then it would be much more. I think it would be much more intuitive because nobody knows what a score is. Nobody knows what that score means except for the technical definition of 1 over the distance from the hyperplane or whatever.
I mean, intuitively, what we can think of it as, it's the same. The farther from the hyperplane, we are more confident.
Ah, there we go. It's not available. Okay, okay. I stand corrected. Thank you.
Yeah, it says probability estimates are not available for loss equals change.
This is a L2 type loss, right? We won't, like, would we get a probability estimate? We won't get, right? For L2.
You can't get it with this method. With
this loss, yeah.
With the SVM, with the support vector machines, linear support vector machines with hinge loss, you can't get it.
It should be like an entropy loss, right?
No, I think the hinge loss is the right one here.
No, I mean, like, if we want probability, it should be like a entropy loss function.
Yeah, like the cross-validation, you know, like cross-validation loss or something. Yeah.
Okay.
Okay. So yes, we just tried that. We don't have that, but that's fine. And okay, so and we get to this graph, and this is what those thresholds look like, right? Because I mean, again, those are not very intuitive, but those are the scores. This is the precision scores. Those are the recall scores, and of course they're all below 1. Okay, and this is kind of how you plot it. Anyone have questions on those plotting functions? Those are relatively straightforward.
Yeah. So to be clear, the you know, the threshold. What does this threshold mean? It means that you're going to decide where to make your classification boundary. In other words, if I set the threshold at, you know, at 0, that means everything that has a score greater than 0 is going to be my positive. I'm going to make it the positive class, and everything that's less than 0, I'm going to make it the negative class. So wherever you set the threshold, that's how you make your classifications. You convert the score into a classification. In other words, you're not accepting the default classifications anymore once you start using the threshold. You're making your own classifications.
And he actually brought up a very important point here. He says, you may wonder why the precision curve is bumpier than the recall curve. And you see here, this is the bumpier parts. And you also see it here, although it's not very obvious. But the reason is that the precision may sometimes go down when you raise the threshold. To understand why, look back at figure 3.3, and that's this one. It basically says, notice what happens when you start from the central thresholds and move it just 1 digit to the right. And when you do that, the precision goes from 80% down to 75%. Because when you move that, the precision actually goes down. just one digit, right? Like just one digit. So 1, 5 right here. Instead of moving 2 digits, but just 1 digit, the precision actually goes down. And to 75%. On the other hand, recall can only go down when threshold is increased, because the false negative will likely continuously decrease when you know, if you like move it, you know, here, when you move it here, when you move it here, the false negatives will continue to decrease. So, cool. Another way to select a good precision recall trade-off is to plot precision directly against recall. And so basically you have all the precision scores, all the recall scores, and you plot them. Recall as X, precision as Y. And you can see that precision really starts to fall sharply around 80%. And that's here, it starts to fall sharply. You would probably want to select the precision recall trade-off just before that drop, for example, around 60%. But of course, the choice depends on your project. So this is where the business case or domain expertise comes in. Like, where do you want to kind of pick a threshold? Okay, but again, like, it's a trade-off. And suppose you decide to aim for 90% precision, you look up the first plot and find that you need to use threshold of about 8,000 to be more precise. You can search for the lowest threshold that gives you at least 90% precision, and using numpy.argmax will give you the index, the first index of that condition happening. And it will just give you the threshold when that happens. To make predictions, instead of on the training set for now, instead of calling the classifier's predict method, you can run this code. And let's check that. And of course, the precision is 90% now, and because we just pretty much picked that threshold. But look how the recall dropped. Great, you have a 90% precision classifier. As you can see, it's fairly easy to create a classifier with virtually any precision you want. Just set a high enough threshold and you're done. But wait, not so fast. High precision classifier is not very useful if its recall is too low. Someone says, let's reach 99% precision, you should ask at what recall, because it's a trade-off. Now, I want to ask, because we're at the ROC curve, do people want to leave this to the next session, or because I mean it's 2-3 pages, and we were already probably half hour past our time.
Yeah.
No, let's leave it till next time.
Yeah, we should leave it till next time.
Okay, cool. Cool. All right, anyone has questions up to this point before we wrap it up?
Thanks so much, Wenqing. Excellent job.
Great, awesome.
Yeah, thank you a lot. Thanks a lot. This was a little bit complicated as well. Like, we need to, I need to do a little bit reading on, a lot of reading on the recall,
actually,
precision and everything.
Yeah, actually, let me share the screen because I want to tell you guys this video is actually really great. At Stats Quest is generally pretty good.
Yeah,
and they have a ROC and AOC video, and it kind of goes through everything and what it means to be like right here at the ROC curve, what it means to be here, what it means to be here, what it means to be there. So it actually explains and also what it means to use AUC, the area under curve. It kind of compares, and it uses the logistic regression as kind of a case, and also so it's very nice to kind of go through this visually, and I think you guys will have a much better understanding of what's going on here.